Okay, right. So this says that what is the advantage of this kind of a theorem? See, this advantage of interpreting Riemann integral as limit is that now if you want to look at the algebra of integrable functions, f is integrable, g is integrable, then you want to look at whether f plus g is integrable or not, right. If you want to go by upper and lower sums, then you have to relate the upper sums of f plus g with the upper sum of f and with that of g. That becomes a bit difficult, one can do that, but now it is being the limit. If I take f plus g, so what will be integral of f plus g? That will be limit of integrals, limit s p f plus g, right. But the limit split, limit of f plus g is equal to limit of f plus limit of g. So that is the advantage, that sometimes this way of proving that is integrable is useful to get the result. So one proves the theorem like this: if f and g are integrable, then f plus g is integrable, and integral of f plus g is integral f plus integral g. So this is via the limit operations, because the left hand side will be a limit of norm p going to 0, right, and that splits into limit of SPF with respect to f, SPF with, because what is the Riemann sum? F plus g at some point ti into the length, so that splits into two parts. So limit of the sum is equal to sum of the limits. So using that, one proves all these results as a consequence of that limiting operation, that if f and g are integrable, then alpha times f is also integrable, and alpha comes out, because in the limit of alpha times something is alpha times the limit. And similarly f and g, right. So if you look at SPF with respect to f will be less than or equal to the Riemann sum with respect to g, because f is less than g, right. The value at a point of ti of f will be less than. So using that criteria of integrability, one proves these things, and this is also not difficult at all, saying that if f is integrable in a to b, then it is also integrable between a and c, in between c is a point in between, plus the integral between c to b, because a partition of the whole interval can be put it as a partition of a to c and c to b, introducing the point c in between, okay. And this is because for an f which is integrable, integral may be negative, okay. So absolute value of the integral is less than or equal to integral of the absolute value, okay. So again, when you look at the limits, right, SPF, you look at the absolute value of the Riemann sums, so that will be less than or equal to mod f at into the length. So this becomes obvious in that case. So using that, that's the very useful result in proving integrability. And not only that, it frees the notion of integrability from function being bounded. Okay, historically it is of great importance, because that gave a lot of interest in looking at what is called Fourier series problem, or in probability and statistics we will find what is the characteristic function of a distribution coming, and looking at their Fourier series problems, okay. So this is integration. So what we have done is, we have given a function f on an interval a b to r, we defined the notion of, geometrically, the notion of area below the graph of the function, right, and that we interpreted as via lower sums, upper sums, or via the Riemann sums.